Hi there, and welcome back to Choose Better Living. This is the space where you and I explore ideas that help us understand ourselves, live with more intention, and become a little better every day. Today, I want to talk with you about a book that offers one of the most comprehensive views of a disease that has caused suffering for millions of people. It is a disease that remains one of the greatest challenges modern medicine has ever faced. That disease is cancer. The book is titled The Emperor of All Maladies, a biography of cancer by Siddhartha Mukherjee. This book is rare in the sense that it gives us a truly panoramic understanding of cancer. It does not look at cancer from only one angle. Instead, it guides us through its causes, its biological processes, and our long and difficult struggle to fight it, from ancient times all the way to the present. This is a book for several kinds of readers. It is for people who have been diagnosed with cancer or who have a loved one facing this disease and who want to understand it more deeply. It is also for those who are interested in the history of disease and how cancer has been treated across different eras. And finally, it is for anyone who wants to understand cancer from a biological perspective, beyond fear and mystery. Before going deeper into the story of cancer itself, it helps to understand the person who tells the story. Siddhartha Mukherjee is a physician of Indian origin and a pioneering cancer researcher. He studied at the University of Oxford, Stanford University, and Harvard Medical School. He has published numerous scientific papers and received major recognition for his research on stem cells, including the National Institutes of Health Challenge Award. The Emperor of All Maladies was his first book, and it went on to win several major awards in 2011, including the Pulitzer Prize for Nonfiction and the Guardian First Book Award. Cancer often feels uncomfortably familiar to us. You may have faced it yourself, or someone close to you may have. It appears in our lives more frequently than ever before. And yet, very few of us truly understand what cancer is. It is not a new disease. Records of cancer appear in medical texts dating back to around 2500 before the Common Era. Since then, countless theories have emerged, each reshaping how we think about this disease and leading us toward what we know today. This book explains the two fundamental biological mechanisms that make cancer deadly. It reveals the internal processes within our bodies and the external factors that can trigger the development of cancer. At the same time, it walks us through the major milestones in cancer research and treatment that have defined our ongoing struggle against this disease. Even though humans have known about cancer for thousands of years, our understanding of it in the past was vastly different from what it is today. Let me take you back to an idea that once shaped all of medicine. Have you ever heard of the concept of balanced temperament? Today, we might use that phrase to describe a successful or emotionally stable friend. But around 400 years before the Common Era, it described a medical theory proposed by Hippocrates, often called the father of medicine. Hippocrates believed that the human body was made up of 4 bodily fluids: blood, phlegm, yellow bile, and black bile. According to this theory, health depended on balance. When one of these fluids became dominant, disease or a certain temperament would appear. For example, a hot-tempered person was believed to have an excess of yellow bile. So where did cancer fit into this system? The earliest known explanation suggested that tumors were caused by an accumulation or blockage of black bile. This idea was developed further by the Greco-Roman physician Galen around the year 160, and it became the dominant theory of cancer for many centuries. However, because human dissection was forbidden for religious reasons, Galen never had the chance to truly test or prove his theory. It was not until the 16th century that this idea began to unravel. The anatomist Andreas Vesalius performed dissections on bodies believed to have cancer and was shocked to discover that neither the tumors nor the bodies contained any black bile at all. Later, in the 18th century, the physician Matthew Bailey also failed to find evidence supporting Galen's theory. Once the black bile explanation collapsed, scientists turned their attention in a different direction. Many began to believe that cancer was caused by external and invisible forces. Until the mid-19th century, theories suggested that parasites or poisonous vapors, known as miasma, were responsible for tumor formation. Worms, fungal spores, and bacteria were all suspected causes. Some scientists believed they had identified these agents by examining cancerous tissue under microscopes. In one of the most striking mistakes in medical history, the physiologist Johannes Weibiger was awarded the Nobel Prize in 1926 for supposedly proving that roundworms caused stomach cancer. He was completely wrong. So for centuries, humanity oscillated between two main ideas. One claimed that cancer arose from internal imbalances within the body. The other blamed external agents invading from the outside. This brings us to an important question. What do we actually know about cancer today? Modern science shows us that cancer develops from our own cells. But unlike normal cells, cancer cells grow endlessly and refuse to die. The idea that cancer was caused by mysterious poisonous vapors now seems absurd. This was exactly what the pathologist Rudolf Virchow thought in the 1840s. Instead of relying on speculation, he chose to study cancer by carefully observing what he could see under the microscope. This approach laid the foundation for our modern understanding of cancer. Virchow's cell theory proposed that every cell comes from another cell. When he examined tumor tissue under the microscope, he discovered that tumors were not foreign objects or invading organisms. They were made up of vast numbers of cells originating from within our own bodies. So what is it really that makes cancer cells so deadly? When you look closely, their danger comes from two defining traits. They do not die, and they never stop dividing. Under normal conditions, your body tightly regulates how cells divide. A healthy cell divides only when it receives specific signals from its environment. It also knows when to stop dividing once growth-inhibiting signals appear. This control system is one of the most essential processes for life. Imagine for a moment what would happen if all the cells in your brain kept dividing without restraint. At first, it might sound appealing if it made you smarter. But in reality, your brain would simply grow larger and larger until it pressed against the skull. The result would be catastrophic. Cancer cells do exactly this. They carry mutations in genes that control growth. Because of these mutations, they divide without needing any external signal. Even when growth-inhibiting substances are present, they continue to multiply. This loss of control is one of the main reasons cancer is so difficult to treat. There is a second trait that makes cancer even more dangerous. Cancer cells do not age, and they do not self-destruct. Normal cells either age and stop dividing, or they deliberately destroy themselves when they become damaged. This process protects the body. At first glance, immortal cells might sound like something wonderful. You might imagine them being used in skincare treatments or anti-aging therapies. But when immortality combines with uncontrolled division, the result is a terrifying enemy. Together, these two traits turn cancer into a force that is extraordinarily hard to defeat. There is no doubt that this disease is lethal. So, where does our modern understanding stand between the two historical theories of cancer? Like Galen, we now believe that cancer originates from within the body. It is a breakdown of the very nature of the cell itself. At the same time, like the supporters of the second theory, we also understand that external agents can trigger cancer. Some chemicals not only cause cancer, they also interfere with the body's ability to defend itself against the disease. To understand this, let me take you back to the 18th century, during the reign of King George. At that time, physicians recorded two unusual deaths involving young boys who developed a rare form of testicular cancer. The question was simple and disturbing. What had caused it? The surgeon Percival Pott investigated these mysterious cases. He discovered that both boys worked as chimney sweeps. From the age of 4, they had been forced to climb naked into narrow chimneys filled with soot. As they sweated, the soot ran down their bodies and collected on the skin of the scrotum. Over time, this constant exposure led to cancer. Pot was among the first scientists to suggest that something as ordinary as soot could cause cancer. Even though evidence supported his idea, many scientists hesitated to accept it. The concept did not fit the dominant theories of cancer at the time. Yet after Pot's discovery, many everyday substances were eventually identified as cancer-causing agents. These included asbestos, benzene, and heavy metals. So, how do these external factors actually contribute to the development of cancer cells? The process unfolds in two stages. First, some toxins can directly alter your genetic material, known as deoxyribonucleic acid. These substances are called mutagens. When mutagens change the behavior of genes that control cell growth, repair, self-destruction, or tissue invasion, a normal cell can transform into a cancer cell. Take benzene as an example. It is a highly mutagenic compound, and most of us encounter it regularly. It can be found in cigarette smoke, gasoline, furniture polish, and sometimes even in carbonated drinks. This means that right now, inside your body, there could already be a mutated cell. That cell might be capable of copying itself endlessly. Under normal circumstances, your immune system would detect and eliminate this dangerous cell almost immediately. However, certain toxins found in heavy metals and benzene can disrupt the immune system. When that happens, the immune system fails to destroy the mutated cell. This is the second stage of cancer development. The rogue cell is then free to divide whenever it wants, eventually forming tumors. Infections can also increase the risk of cancerous mutations, especially when tissues are repeatedly damaged and forced to repair themselves. When you think about infection, what comes to mind first? Maybe a runny nose, a cough, or a sneeze during the winter months. But not all infections are harmless. Some can lead to cancer. This connection was first discovered through studies in birds. A poultry virus researcher named Peyton Rouse was experimenting with a rare epithelial cancer found in chickens. When he transplanted cancerous cells into healthy chickens, tumors developed as expected. Then Rouse took the experiment further. He prepared another sample from the tumor and removed all the cancer cells. What remained was a filtered extract. When he injected this extract into healthy chickens, they also developed cancer. This result was astonishing. It showed that an infectious agent, later understood to be a virus, could transmit cancer without transferring cancer cells themselves. Once again, our understanding of cancer expanded. It was no longer only a matter of internal cellular failure or chemical exposure. It also involved infections that could quietly reshape the biology of cells over time. Rouse eventually concluded that something extremely small had passed through his filter and transmitted cancer. Only one kind of organism fit that description. It had to be a virus. You might feel that you have little in common with chickens, but the connection between cancer and infection is something both humans and animals share. In the human body, infections can lead to cancer in two main ways. First, microorganisms can indirectly create conditions that favor cancer. Some viruses cause chronic inflammation, which significantly increases the risk of cancer. But why does this happen? Inflammation damages infected cells. At the same time, surrounding cells begin to divide aggressively to repair the injured tissue. Each round of cell division carries the risk of a copying error, an accidental change in the cell's deoxyribonucleic acid. That single mistake can turn a normal cell into a cancer cell that divides uncontrollably. Another example comes from a bacterium called Helicobacter pylori. It lives in the stomach and causes chronic gastritis and peptic ulcers, damaging the stomach lining over time. As stomach cells repeatedly divide to repair this damage, mutations can occur in their genetic material. In some cases, these mutations eventually lead to stomach cancer. Beyond indirect effects, some viruses can cause cancer by directly altering a cell's genetic code. One well-known example is hepatitis B virus. It can insert its own genetic material into human cells and activate genes that promote cancer development. That said, it is important to keep perspective. Most cancers are not caused by infections, and most infections do not lead to cancer. You do not need to worry about getting cancer from shaking someone's hand. As our understanding deepens, it becomes clear that infection is only one part of the story. Radiation, hormones, and genetics also play major roles in shaping cancer risk. Have you ever heard of the Radium Girls? They were not a pop group. They were a group of women in the 1910 era who were hired to paint luminous watch dials using radioactive paint that contained the element radium. Tragically, this job turned out to be deadly. A few years later, their jaws began to deteriorate and they developed cancers of the mouth, neck, and bones. Even worse, many of them developed leukemia. Radiation was later proven by science to be a powerful cause of cancer mutations. In the 1920s, the Nobel Prize-winning chemist Hermann Muller demonstrated this by exposing fruit flies to X-rays. The number of mutations in these flies increased dramatically as a direct result. In the human body, radiation damages cellular deoxyribonucleic acid, causes mutations, and can eventually lead to cancer. Alongside radiation, hormones within the body can also increase cancer risk. You might remember that we learned cancer cells respond abnormally to growth signals. This abnormal response does not apply to sex hormones because these hormones act as signals for both normal cells and cancer cells. For example, any breast tissue will grow more rapidly in the presence of estrogen, regardless of whether the cells are healthy or cancerous. As a result, certain tumors can grow under the influence of estrogen. The third major factor influencing cancer risk is something you are born with: your genes. This is why some cancers run in families. A well-known example is the BRCA1 gene, which can be inherited and significantly increases the risk of breast and ovarian cancer. A healthy BRCA1 gene helps repair damaged deoxyribonucleic acid in breast tissue. A mutated version cannot. When damaged cells fail to repair properly, some survive with errors. Over time, these errors accumulate and can turn cells into cancer. About 1 in 100 women carries a mutated BRCA1 gene. In the worst-case scenario, these three factors can work together. A woman may inherit a mutated BRCA1 gene. She may be exposed to heavy metals that weaken her immune system, preventing it from eliminating early cancer cells. At the same time, estrogen may fuel the growth of developing tumors. Long before we understood any of this, humans were already trying to treat cancer. Since ancient times, surgery has been the primary approach. But the consequences were often brutal. If modern cancer treatment feels complex, imagine what it was like around 500 years before the Common Era. At that time, Queen Atossa of Persia discovered a lump in her breast. Terrified, she isolated herself from everyone except a trusted slave named Democedes. He persuaded her to allow him to cut out the tumor and then treat the wound. In theory, what Democedes did aligned with the earliest surgical approach to cancer. The first goal was to remove the main tumor, ideally before the cancer spread to other parts of the body. If cancer cells had already spread, surgery was used again to remove newly formed tumors. Even today, surgery can be used preventively by removing tissues such as colon polyps or moles before they become malignant. In reality, Democedes lacked two critical tools that modern surgeons rely on: anesthesia and intravenous fluids. Effective anesthesia was not discovered until 1846, when the dentist William Morton demonstrated that ether could induce unconsciousness. Before that breakthrough, surgeons attempted to numb patients using alcohol or opium, but the results were unpredictable and unreliable. Modern anesthesia techniques now allow surgeons to perform operations lasting several hours, something that would have been unimaginable in ancient times. Even when patients in the 19th century survived their brutal surgeries, many of them later died from infection. It was not until around 1860 that Joseph Lister introduced antiseptic surgery using phenol, also known as carbolic acid. This was one of the first effective sterilizing agents, and it fundamentally changed surgical practice. Around this same period, Some physicians pursued extremely radical approaches to cancer treatment. In the late 1800s, the surgeon William Halsted believed that breast cancer could be cured by destroying every single cancer cell in the affected area. This approach did not only involve removing the breast itself. It also required removing the chest muscles that allow the arm and shoulder to move, along with the nearby lymph nodes. This aggressive form of surgery did help reduce the risk of cancer coming back locally. However, it was useless once cancer had already spread to distant parts of the body. Surgery, no matter how extreme, had clear limits. As our understanding deepened, it became obvious that another kind of weapon was needed, one that could reach cancer cells a surgeon's knife could not. Chemotherapy emerged as that weapon, designed specifically to stop the rapid division of cancer cells. Surgery remains a vital tool in cancer treatment, but it cannot eliminate cancers of the blood, such as leukemia, or remove tumors that have spread widely throughout the body. To target fast-dividing cells that cannot be cut out, we rely on chemotherapy. The first thing to understand about chemotherapy is how it works at a fundamental level. Chemotherapy damages the deoxyribonucleic acid that controls cell division. It stops cell proliferation in all affected cells, but it has a stronger impact on cancer cells. In this process, chemotherapy attacks both healthy and cancerous cells. The difference is that normal cells are able to recover, while cancer cells often die. One of the earliest chemotherapy agents has a dark history. Sulfur mustard was originally developed as a chemical weapon during the First World War. Today, modified versions called nitrogen mustards are used to treat leukemia and lymphomas. They work by reducing the number of cancer cells in the lymph nodes, bone marrow, and blood. Another form of chemotherapy does not directly damage the deoxyribonucleic acid of cancer cells. Instead, it disrupts their metabolism. These drugs are known as antimetabolites. They mimic the nutrients that cells need to survive and divide. But instead of nourishing the cells, they sabotage them. In simple terms, these drugs imitate essential building blocks required for cell division, but they fail to perform the proper biological function. Take folic acid as an example. It plays a central role in cell replication. When a cancer cell is tricked into using an antifolate compound instead, it can no longer replicate its deoxyribonucleic acid. Cell division stops, and tumor growth is halted. In fact, antifolates were among the first drugs successfully used to treat leukemia. These are just a few examples from the wide and varied family of chemotherapy drugs. Despite their differences, they all succeed in one shared way. They block the unlimited division of cancer cells. But when surgery and chemotherapy are not enough, another option comes into play. You may remember the radium girls and the disfigured jaws that revealed how radiation can cause cancer. What may surprise you is that radiation can also be used to treat cancer, for the very same reason. Radiation damages deoxyribonucleic acid. Radiation therapy uses carefully controlled high-intensity beams to destroy cancer cells that have spread within a specific area of the body. For example, one of the most common childhood blood cancers is acute lymphoblastic leukemia. This cancer often responds well to chemotherapy. However, some cancer cells can hide in the brain, where chemotherapy cannot easily reach them. Because these cells are spread throughout the brain, surgery is not an option. In these cases, radiation therapy is applied to the brain after chemotherapy. Treatment involves directing high-energy beams at the patient's brain several times a week over the course of multiple weeks. The procedure itself is not very painful, but it can cause fatigue, nausea, and hair loss. Even so, radiation therapy can dramatically reduce the risk of cancer returning. Radiation therapy is also effective at eliminating tumors that cannot be removed through surgery. It can reach areas that a surgeon's knife simply cannot access, without putting the patient's life at risk. This is why radiation is so valuable when dealing with critical regions of the brain. Surgical removal may be impossible, but radiation remains an option, because carefully controlled beams can target cancer cells without causing the same level of damage as an incision. For this reason, radiation therapy plays an essential role in cancer treatment when other methods cannot be applied. Still, it is not considered a last resort. Instead, cancer treatment often relies on combining multiple approaches, using each method where it is most effective. As the 20th century unfolded, the fight against cancer took an unexpected turn. Two very different individuals would come together and reshape how the world confronted this disease. In the 1940s, a pathologist named Sidney Farber locked himself inside an underground laboratory in Boston for days at a time. Meanwhile, a woman named Mary Lasker lived a very different life, surrounded by the spotlight as a successful businesswoman in New York. At first glance, they seemed like an unlikely pair in the battle against cancer. In 1947, Farber discovered that anti-folate drugs could be used to treat childhood leukemia. Because of this breakthrough, he is often regarded as the father of modern chemotherapy. He was also known for his pioneering approach to caring for children with cancer. Farber understood that life with cancer was not only physically painful, but also emotionally overwhelming. As a result, he devoted enormous effort to building support systems for caregivers and providing counseling for patients and families. Still, the needs of cancer patients could not be met by Farber alone. In 1948, he founded the Children's Cancer Research Foundation. Although the foundation raised significant funds, it was not enough. Farber needed sustained financial support and a large-scale public campaign to move cancer research forward. At the same time, Mary Lasker had recently revitalized the American Cancer Society by launching major fundraising efforts through Congress. She was an expert in public relations and political advocacy. What she lacked was a strong scientific and moral partner to give her movement greater credibility and direction. Naturally, Farber and Lasker found each other. Each had exactly what the other needed. Over the next 20 years, they formed a powerful partnership. Their greatest achievement came with the National Cancer Act, signed into law by President Richard Nixon in 1971. This act allocated $1.5 billion for cancer research. Today, much of what we know about cancer exists because of their work. However, Farber and Lasker focused primarily on treating cancer and developing drugs, rather than conducting basic research into the origins of the disease itself. As a result, it was not until the 1990s that scientists fully understood that cancer is driven by genetic mutations. This realization led to an entirely new approach to treatment. This new direction centered on gene-based therapies. The goal was to repair malignant genes, restore them to normal function, or at least disable the abnormal growth signals they produced. As I reflect on the central message of this book with you, one idea stands out clearly. Cancer is complex. But thanks to decades of research and breakthroughs from the past, we now have a solid foundation for understanding how normal cells transform into cancer cells. And because of that foundation, the future holds the promise of deeper advances and new approaches to destroying, treating, and ultimately preventing cancer. This is not a story of a final victory. It is a story of progress built step by step. And it reminds us that knowledge itself is one of the most powerful tools we have in learning how to live better, even in the face of one of humanity's most formidable diseases.